Have you ever stopped to think about what a skyscraper and, say, a soap bubble actually have in common? Well, the answer is a lot less than you'd think, but also way more than you can imagine. Today, we're going to peel back the layers of the world all around us, from the boxes we stack to the planets we orbit, to find the really simple core ideas that define pretty much everything. And let's be honest for a second. Opening a math textbook can sometimes feel like you're trying to decipher an ancient alien language, right? But what if I told you that some of the most profound ideas in geometry are actually, secretly, incredibly simple? That's what we're going to dig into.
Yeah, nope. We are not doing that today. Instead of getting totally bogged down in complicated proofs and formulas, we're just going to look at these shapes for what they really are. Beautiful, totally intuitive concepts. And, hopefully, have a little fun with it.
Okay, so let's start with the one big question that's going to unlock everything else for us. What is the fundamental difference, the actual DNA that separates one kind of shape from another?
Just look around you, right now, wherever you are. I bet you can spot dozens of these shapes. But they almost all fall into one of two big families. You've got the blocky, straight-edge crew like boxes and buildings, and then you've got the smooth, perfectly curved family like balls and bubbles. So what's the core idea behind each one?
All right, let's jump into family number one, the prism. You've seen these things a million times, but its true identity, its big secret, is almost laughably simple.
So, to really get what a prism is, first you got to know what a polyhedron is. And please, don't let the fancy name intimidate you. Polyhedron is basically just Greek for many faces. So if you have a 3D shape that's made up of flat sides with no curves at all, boom, it's a polyhedron. That's the only rule to get into this club.
So how do you make one of these prisms? It's so simple. Just start with any flat shape you can think of. A triangle, a square, whatever. Now, imagine you make an identical copy of it and just let it float right above the first one. And the last step? Just connect the dots. You connect the matching corners. See, you're not really building a shape, it's more like you're stretching it. You're pulling a 2D shape up into the third dimension.
And take a look at this hexagonal prism right here. It's really nothing more than a hexagon on the bottom, the exact same hexagon on the top, and then just a bunch of rectangles connecting the sides. At its heart, it's just a stack.
What's great about this is that it gives us a ridiculously easy way to name them. You don't need some advanced degree, you just have to look at the base shape. Is the base a triangle? Well, then it's a triangular prism. Is it a pentagon? You guessed it, pentagonal prism. You get the idea?
And this whole stacking logic makes finding the volume an absolute breeze. You just have to ask two simple questions. First, how much space does that base shape take up? That's your B for base area. And second, how high is the stack? That's H for height. You just multiply them together and there's your volume. It's just so elegant.
Okay, let's shift gears completely. Let's look at the second family of shapes, the sphere. Now, if the prism is all about stacking flat things, the sphere comes from a totally opposite idea, and in some ways a much purer one. Okay, forget stretching, forget stacking. To make a sphere, you only need one thing. A single point just floating in the middle of empty space. Now imagine every single possible direction from that point, and you place another point exactly the same distance away, let's say 5 inches. The infinite collection of all those points you just made, that forms the perfect surface of a sphere. And that 5-inch distance, well, that's what we call the radius. So here you have it, the two ideas side by side. On the left, you've got the world of prisms, built from polygons, full of flat faces and sharp edges. And on the right, you've got the sphere, defined by a single center point, which gives it one continuous, perfectly curved surface. These are two totally different ways of thinking about shape.
And hey, here's a fun little piece of math trivia for you. Technically speaking, when we say sphere, we're really just talking about the 2D surface, like a soap bubble. If you want to talk about the solid object, the inside included, the proper term is actually a ball. So technically, the surface of a basketball is a sphere, but a solid bowling ball is a ball. There you go. Now you can win your next trivia night.
Now, the sphere's volume formula, it really shows you where it comes from. There's no base or height here, right? It's all about that single central point. The formula, 4/3 times pi times the radius cubed, tells you that the sphere's entire being is just defined by its radius, and of course that mysterious amazing number pi. Okay, so we have our two big ideas, stacking and perfect symmetry. But this is where things get really cool, when we start pushing these simple definitions to their absolute breaking point.
Let's go back to our prism for a second. We know we can build one with a base that has 3 sides, or 6, or 20, or whatever. But what if we just keep going? What happens to the shape if its base has 100 sides, or 1,000? What would happen if we could give it an infinite number of sides?
Well, as you can see, the more sides you add to that base, the less blocky the prism looks. It starts getting smoother, rounder. I mean, a prism with 100 sides would look almost perfectly round. So what happens at that logical extreme, a base with an infinite number of infinitely tiny sides? Well, what you've created is a perfect circle. And what do you call a prism that's built on a circular base? A cylinder.
And there it is. That's the huge aha moment. A cylinder isn't some totally separate, weird category of shape. It's just the final evolution of a prism. It's what happens when you take that simple stacking idea all the way to infinity.
Okay, so we found the prism's ultimate form by adding infinite sides. But what about the sphere? It doesn't have any sides to add. So to stretch its definition, we can't just tinker with its shape. We have to change the very space that it lives in. We have to go to another dimension.
Everybody, meet the hypersphere. Now the idea here is exactly the same as our normal sphere. It's all the points that are an equal distance away from a central point. The only crazy difference? It exists in four-dimensional space. Now while we can't build one or really even picture it in our heads, we can describe it perfectly with the language of math. It's just the logical next step for a sphere, a journey into a higher reality.
So, we've gone through prisms, cylinders, spheres, and even mind-blowing hyperspheres. So why does any of this matter? Well, it matters because these two incredibly simple root ideas, stacking a flat shape and radiating from a central point, are basically the fundamental architectural principles of our entire universe.
Let's just put it all together. The prism, which is born from stacking, gives us the flat-face language of human creation, our boxes, our buildings, the crystals we find. And the sphere, which is born from perfect symmetry, gives us the curved language of nature, planets held together by gravity, or soap bubbles held together by surface tension. One is kind of the geometry of a blueprint. The other is the geometry of physics.
And that just leaves us with this one fascinating final thought. If these two simple geometric ideas, one about stretching a shape and the other about symmetry around a point, can explain so much of the world we see, from the tiniest crystals to the biggest planets, what other simple fundamental rules are just out there, waiting for us to discover them?